Okay, so today we'll finish up some issues related to LR1 parsing, and in fact it happened that two of these issues are related to midterm questions. Okay, so the first question, there was a question in the midterm about the if statement. So a statement could be an assignment or an if. Okay, and of course we know what the assignment is. The if is going to have an optional else. So we have an if with a condition, and then after the if we have some let's call it code, and there is an else, some code, and or you can have an if without an else. So you can have a condition with code and no else. So the else is optional. Of course, this code, so this is one way of doing this. The code could be just a single statement, or a statement list between braces. It's just a single statement. Of course, this is one way of doing it.
Yeah, but you could also have according to the, if I recall correctly from the midterm question, you could also have a single statement inside braces too.
Yes, we haven't defined statement list, because we can define statement list to have a single statement. So statement list, in fact, you can define statement list to have an possibly empty. So it can be, you can recurse on statement. So it's statement list statement, or epsilon. So this allows you to put as many statements as you want, and you can also put no statement. So this means that between the braces you can have an arbitrary number of statements. Of course, I graded only 4 questions in the midterm. The first 4 questions, I graded this question, and in fact only a few students got this completely correct. The part that most students missed is this. Most student grammars did not allow a single statement to be the code after the else. Most students missed this. An optional else, most students did this right. So most students allowed the if statement to have an else or not to have an else. The else was optional, but many students missed this part. Anyway, so this is the solution to the exam question. In fact, this is the new part, the thing that we did not cover in class. The condition, we did it in the review session. So the condition is exactly what we did in the review session with that Boolean and with the precedence between and or. So that was done in the review session, and I was expecting 90% of the students to get it right because it was done in the review session, but the percentage of students who got it right was not 90%. It was less than 90%, although it was done in the review session. So it was exactly what we did in the review session for the condition. Okay, so now what's the point? Well, this is for the test, but if-else statements are interesting when it comes to parsing, because a grammar with if-else, this grammar is ambiguous. Why is it ambiguous? If we have something like this, if let's say condition, if some condition, we have statement 1, if condition do, or no, it's the example that will show this. If condition if condition 1, if condition 2, then do statement 1, else do statement 2. Okay? So now, let me just, to simplify this, let's assume that we have a single state, just to get to the point. So let's replace this with statement. Let's replace this code with statement, just to simplify the example that we are about to study, just to focus on the point. So if you have something like this, if condition 1, if condition 2, do statement 1, else statement 2. Now, where is the ambiguity here?
Where is the else attached to? Is it the first if or the second?
Yeah, exactly. So is the else attached to the first if or to the second if? So there are two derivations of this, two possible derivations. Ambiguity means that you can come up with two possible derivations. So in the first derivation, by the way, the languages that you are familiar with, what do they do? Which one is, will the else get attached to the first if or the second if?
It's the second if.
The second, yeah, the innermost if. So what we are familiar with is this. Okay, so this is going to be a statement. So one derivation is this. Statement is an if, of course, condition. I'm going to drop the parentheses just for simplicity, okay? If condition, then statement, and this statement, sorry, I also dropped so let me put the if. So it's statement is an if, and if is if condition. I can do this. I don't want it to get messy. If condition statement, then this statement is another if, and this if is if condition, then statement, and else statement. Okay, else. And so this is one possible parse where this is condition 1. So this condition is going to be condition 1. This is condition 2. And this is statement 1, and this is statement 2. The other possible parse, another possible parse is statement is an if, and the if is, what should we substitute for if now?
If condition statement else.
Yeah, exactly. So at the top level, we have an if else. So if condition, then statement, else statement. Okay? And how do we complete this derivation?
The statement in the if gets another if?
Yeah, so this statement here is this. This is a statement now. So this if condition statement, this statement is an if, and this if is if condition statement. Okay, so now this is condition 1, this is condition 2, and this is statement 1, and this is statement 2. So now here, the else is associated or is an else for the innermost if. Here, the else is for the outer if. Okay? So two possible derivations. So this is the if-else, the if-else ambiguity. Now, how does this reflect on parsing? So on parsing, when you are doing, let's do, with LR1 parsing, when we are doing LR1 parsing, at some point, this is our, with this grammar, with the placeholder, the placeholder is going to start here. And then our placeholder is going to move. And then it will get to this point. So the placeholder is going to move, right? In LR1 parsing, we have a placeholder that keeps moving. The placeholder will, at some point, will get at this point. So you will have something, you will get, in some state, you will get if is an if condition code else code and you will get if condition code without else, and at some point the placeholder will get to this point. If what we have on the stack is this, if this appears on the stack, if this is what we have on the stack, then the placeholder will get to this point. Now, by the way, what's the look ahead? The look ahead should be,
well, in the first one, the look ahead will be else. The second one should be end of line.
Not necessarily. In fact, what can come after an if in this grammar? In this grammar, what can come after an if?
Trying to see. Trying to see if you look at the condition.
Well, first of all, if here, this is the start variable. So after if, you can always have an end of file, because an if statement can always be the last state according to this grammar. This is a grammar that says, okay, what you are parsing is a single statement. Your start variable is a statement, so what you are parsing is a single statement. And this statement is either an assignment or an if. So the if can have end of file. Okay? But since the if, because this can be an if too. So when we do the expansion, when we did the expansion in state 0, the if here, because this could be an if can be followed by an else. So in generally speaking, an if statement can be either followed by an else or it can be followed by an end of file. So in fact, your look ahead here is going to be else or end of file. And here it's going to be else or end of file. So basically, if an if statement is followed by end of file, if it's the complete statement, and it's followed by an if it's this if. If we can, if this is an if, then this whole thing, this is an if, then it's going to be followed by an else. Now, when we construct the table, when we construct the LR1 table for this, so this is one of the states. This will appear at some state. Of course, this is not going to be the start state. We will not get to this. We're not showing all states here. We will get to this when the placeholder moves past all of these and gets to this point. But this is the point where we will hit a problem. Because at this point, Do we have a reduction?
Yes.
Yeah, we have a reduction. So this is a reduction. So we can reduce by rule number, we didn't give it a number, but let's say 0, 1, 2. So we can reduce by rule number 2, which is this. But do we have a shift?
Yep.
Yeah, we also have a shift. So the problem here is that when you get to this point and if what you are seeing in the file is an else, if your look ahead is an else, you can reduce or you can shift. So this is what we call shift reduce error. So there are two possibilities. And this is just not good. So this is a shift reduce error. So it's a shift reduce error because we can shift or reduce. And in fact, if we shift, we will get one of these derivations. And if we reduce, we will get another. If you think about it, shifting will give us this or this. So will shifting give us the first one or the second one?
Shift will give us the first one, I think.
Yeah. If we shift, we'll get the first one. Because if we shift, we are waiting. We are not reducing until we get here. So if we shift, it means that we're not reducing at this point. We will wait until a later state when the placeholder gets here. And then we're going to reduce. And our reduction here is going to reduce this to a statement. So if we shift now and reduce later, we will get this reduction. This will become an if or a statement, which is a statement. And then this will give us this derivation. So shifting will give us this derivation, while reducing will give us the other derivation. Reducing, it means reduce immediately. And when you reduce immediately, you will get this derivation. So this is a shift reduce error. Now, how is this handled in practice? Now, when we have a shift reduce error, strictly speaking, this means that this grammar is not an LR1 grammar. It means that it cannot, strictly speaking, it cannot be parsed using the LR1 parsing algorithm. But in fact, if we can just choose between shift and reduce, we can proceed. So it's a matter of choosing whether we want to shift or reduce. And in this case, if we choose to shift, we will get the expected behavior, or we will get the expected derivation. So you will be using a parser generator program. You will be using Bison for to generate a parser. And when you have an if-else, it will, when you write a grammar for an if-else, it will tell you that there is a shift-reduce error. And the default is to resolve the conflict in favor of a shift, to do a shift rather than a reduce. Okay, so this is the default behavior. In fact, I think it even, if you disable warnings, it's not going to give you a warning. It will just do the default resolution of the conflict, which is resolve the conflict in favor of a shift rather than a reduce. Okay, so this is just to be aware of the shift reduce error, and it's a typical example for this is the if-else statement. Any questions on this?
I got one.
Okay.
On the second one, why have else as a look ahead? Because that second one's not, the if isn't followed by an else.
Well, in fact, we don't know. We can't tell the look-aheads by looking at these. The look-aheads are determined in. We're not showing the whole LR1 construction here. So the look-aheads come from the initial state. So it comes from the top. So in order to answer this completely, I have to show the whole LR1 states, all the LR1 canonical collections. And there are like 14 or 15 states in this case.
Yeah.
Okay. Yes. Yes.
Say that ambiguity in general does not make a grammar unparsable.
Yeah. So in general, yeah, you can sometimes find a way to get around ambiguity or to handle ambiguity.
Okay.
So an ambiguous grammar is not necessarily bad, and it's, an ambiguous grammar is not necessarily unparsable, because they exist. All languages have if-else, and people write grammars and build parsers for them, and everything works fine. Okay, so this is one question. The other question that I hope I will get to finish is the LR1 parsing. So the LR1 parsing question. So the goal is A, and A is AA or A, small a. So is this a right recursive or a left recursive grammar?
Right.
Yeah, this is right recursive. Yeah. Because many people were still in the exam, many people were confused. Some people in the LL1 parsing question, some people tried to remove left recursion from a grammar that doesn't have left recursion. It does not have left recursion. So, and some people are trying to remove left recursion. So left recursion is when you have, this is the left recursive version of this grammar that we did in class. Goal A, and A is AA, and A is A. So this is what we did in class. We did the left recursive version in class, and in the test I asked you to do the right recursive version. The right recursive version is totally different. The solution is going to be totally different, but it is still small. It is still a manageable number of states because it's a small grammar. So the number, we have only these productions. This is 0, 1, 2. And again, the initial state S0 is going to have goal A. What's the look ahead? It's always end of file. Then we expand A. We expand for A. So A is AA end of file, or A end of file, and we are at the beginning of an A. So this is our first state. Now, is there any further expansion? No. No further expansion. Why? Because this is a terminal. So this is a terminal, so we just stop. This is our start state. Now we have obviously two transitions, one on big A and one on little a. So let's do it systematically the way we did it in class. The transition on big A is going to give us this. The transition on big A is going to give us goal, big A, placeholder, end of file. Is there any expansion, further expansion of this? No further expansion. But this is a reduction. So this is a reduction, which is an accept, in fact. Now, the transition on little a, trying to save some space, transition on small a will give us, again, the placeholder moves, A dot A, end of file, A, end of file. We just move the placeholder. Now, do we have any expansion? Yes. So a huge number of people missed this expansion. So we have an expansion on A. This is a non-terminal. So we expand on A. And expanding on A is going to give us A, AA, and A goes to A. So we have to expand this. Now, what's the look ahead?
End of file.
Again, the look ahead is what follows an A. So what comes after an A? Here is an A that we are expanding. We're expanding this. So this is an expansion of this. It's like this is going to get substituted for this. What comes after this is end of file. What comes after this is end of file. No, it's not an A. It's an expansion for A.
Oh.
So what?
Okay.
So it's an expansion, right? That's why we call it expansion. So A is replaced with this. So what comes after the A is an end of file. And this is an end of file. Okay? So this is the expansion. Now, any further expansion? No, because this is a terminal. So this is what we get. So this is state 1. This is state 2. Of course, this will not lead to any further state. Will this lead to any further states?
Yeah.
Yeah. In fact, we have a we have a transition on big A and on little a. On big A, if we have a big A, then this is going to be A placeholder end of file. Anything else?
Nope.
No, because we only move it past the A. So this is where the placeholder precedes an A. So this gives us this. Any expansion? No expansion, because the placeholder is at the end. So this is our state. And we call this state number 3. And we have a reduction.
Yeah.
Yes, we do have a reduction. So this is a reduction by
R1.
rule number 1. Now, what if we have a small a here? So if we have a small a, we will get A goes to, well, here it's, so these are the ones that are going to move past the small a. So it's going to give us A dot A end of file, and A is A dot end of file. Is there an expansion? Yeah, so it's going to expand the same thing to A end of file, A dot A end of file. But this state is the same as state 2. So it's not a new state. So basically, we have a loop into the same state. It's not a new state. Yeah.
How did you get capital A again? Sorry, what's that?
Which one?
On the third line for the last day we just did.
The third line?
Yes.
By expanding the A. So always, we said whenever you have a state, the first question is there an expansion? Second question is there a reduction? So we did this. Is there an expansion? The answer is yes, because this is a non-terminal. So we expand the A.
Yeah, I think what you mean is you wrote it wrong.
Yeah, it's transposed big A and little a on the third
Yeah, you
line. in
switched
state
them.
4.
It's not part of the rules.
Oh, this.
You wrote it wrong.
Sorry.
Okay.
Okay, so it's going to be the same as this. Yeah. Sorry. Yeah, so this is an expansion of A. Oh, sorry. So that was my fault. Okay. Yeah, so you'll get the same state. So so always, ask yourself whether there is an expansion or not. And here you will get the same state. So this is a loop back into state number 2. Okay. Now, so we just don't need this. So now the go-to is going to be the go-to table and the action table. So let's put the go-to here.
We're missing a reduction, though.
Got the reduction.
Yeah, we will find it.
We don't have a reduction for rule 2.
It's in S2.
It's in state 2. Yeah.
Yeah, we'll find it. We'll catch it. Yeah, so we have a reduction here on end of file, and this is R2. Okay. So let's do the goto. The goto from state 0, state 1, state 2, state 3. So there are only 4 states. So the only reductions that we have on non-terminals, we have a transitions. A transition from S0 to S1 on an A, S0 to S1. And we have a transition from S2 to S3 on an A. And that's it. This is the goto. Now our action table. The action table is going to look like this. This is S0, S1, S2, S3. And this is an end of file, and this is an A. And again, S0, there are no reductions, but there is a shift on an A. So if you are on an A, you shift and you go to S2. If you are in S1, there is a reduction if the end of file, if the look ahead is end of file, so you accept on end of file. No transition out of S1. S2, there is a reduction R2 on end of file. End of file, you do R2, and there is a transition on an A. The A leads to the same state, so shift and stay in the same state with an A. Now S3, there is a reduction. If the look ahead is end of file, you reduce by rule number 1, and there is no transition. So this is our action table. Oh, let's okay. Yeah, let's do the stack, because the whole point here is the stack. So the stack is going to be first S0 and S0 and the look ahead. And here's the look ahead. So we have A. So S0 on an A, it asks you to shift by 2. So you'll do a shift 2. And shift 2 gets you S0, A, S2. And now we have shifted. Again, I am in S2 and seeing an A. So it keeps telling you that if you are in S2 and you are seeing an A shift, S0, A, S2, shift again, S2. Okay, and you tell it again, I'm in, so we shifted twice, so we are here now. Now, again, S2 and A tells you to shift again. And now you have S0, A, or I think we'll have, let me give myself more room on this, because now we have S0, A, S2, A, S2, A, S2. We shifted 3 times. Now, after shifting 3 times, we are here. And we are seeing end of file. So after shifting 3 times, we shift 3 A's. OK, now you look up the action table. I am in S2, and I am seeing when I was seeing an A, I was shifting. Now when I'm seeing end of file, it tells you to reduce by rule 2. So now you reduce by rule 2. An R2 and an R2 is going to do this. How many symbols do you pop off?
2.
Rule number 2, no. Rule number 2 has 1 symbol.
Oh, wait,
2 times the
Yeah, so yeah, okay. So yeah, exactly. Yeah, so so there is only 1 symbol, so you pop off 2. So you pop off these. the A with the state number. So you get S0, A, S2, A, well, this is, and S2. So now what's our base state for the goto? Our base state for the goto is whatever we have after we pop off. So after we pop off, our base state is S2. So we need goto of S2, which is our base state after popping off, and the symbol that we get, which is an A. And this is S2 and A. This is an S3. So this means that we go to S3. This is an A, and this is S3. I think this is the most important step in the in tracing the parsing algorithm on the stack. So again, you pop off. Your base state is S2. Go to of S2 and A. And what's the rationale here? The rationale is that you go to your base state because you have replaced the A. You replace the A with an A. So now we are looking for a transition on big A because you replaced the A with a big A. So that gets you to state number 3. Now you are in state number 3 and you are seeing end of file. It tells you to reduce by rule number 1. So reduce by rule number 1. Now how many do we pop off?
4.
We pop off 4, yeah. S0, A, S2. So we pop off this 1, 2, 3, 4. Again, this is our base state, which is S2. So go to of S2 and the symbol that we get, which is again an A. And this is going to take us to S3 again. So we put the A and we go to S3 again. Now it's going to tell us the same thing because we are in S3 and we are seeing end of file. So it's going to say reduce by 1 again. So reduce by 1 again is going to do this. This is S0. Reduce by 1. So we pop off 4. So again, our base state now is
S0.
S0. Yeah. After you pop off these 4, your base state is 0. So now we need go to of S0 and A, because we will get an A. And go to of S0 and A is S1. So we put an A and we go to S1. Now, the action table, we are in S1 and we are seeing end of file. It says now accept. Okay, so now we accept S0, and this is the goal, and accept. Okay, so in fact, this is the exam question. I don't think it's harder than the one that we did in class, but it's just different. So it's different, and if you really understand the procedure, you shouldn't have a problem with this. But if you're having problem, then you don't understand the procedure very well. So
I think what kept screwing everyone else up was the part that it kept looping back on state 2. Is I think is what screwed everyone.
But there was a homework question in which there is a, you encounter the same state again and you don't create a new state. So there was a question on purpose. There was a question in the homework on the classic expression grammar where you encounter a state that is not a new state, okay, and you don't, when you encounter the same state, you don't create a new state. So yeah, so there was a homework question, the classic expression grammar. So how many people went through the homework? After I posted the solutions to the homework 2 and 3, how many people went through the solutions before the midterm? Are you sure? Well, I was expecting everyone to go through the solutions. And in fact, even to watch the lectures again, because it's we'll talk about LL1, because on LL1 the performance was even worse than LR1, which was against the expectations. But let me finish this point first, because here there is a point that we're trying to make about left recursion versus right recursion. So the one that we did in class was goal A, then A is AA, and A is little a. So we did the left recursive one. So now what do you think? Do you see anything weird here or inefficient with this? Yeah.
So with the one we just did, it kept shifting all the way to the end, and
Yeah.
then it did reductions.
Yes, exactly. So if we had, instead of 3 A's, if we had 1,000,000 A's, then it would have shifted 1,000,000 times. And it would have put 1,000,000 symbols, in fact 2,000,000 symbols on the stack. So the point here that we are trying to make is that when you apply LR1 parsing to a right recursive grammar like this,
You have the same problem with the L1
Yeah.
with a left recursive grammar.
Yeah, left recursive grammar. LL1 has its problems with left recursive grammars. In fact, it cannot do left recursive at all. So LL1 parsing cannot do left recursive grammars at all. LR1 parsing can do both. It can do left recursive and right recursive, but with the right recursive ones, it has this, stack problem. It may do a lot of shifting, and it may make the stack grow really big. You can have a really big stack when you apply LR1 parsing to a right recursive grammar. This is the point. Yeah.
Right, so if you have a known right recursive grammar, would the solution then be to read it from right to left?
What do you mean known?
Like if you're building the LR1 parser and you know that the grammar is a right recursive grammar, could you solve this problem with pushing 2 million things on the stack by having the parser read the string from right to left?
Well, this is an algorithm. So you have to. This is the algorithm, the LR1 parsing algorithm. So this is, we just followed the algorithm systematically, and this is what it gave us.
Okay.
So it, remember always that the algorithm is as intelligent as you can make it. You make the algorithm. So this algorithm is just algorithms. Don't expect an algorithm to be like human beings. Oh, okay, let me see. Oh, this is not good, so let me change myself. The algorithm doesn't change itself. So you design an algorithm, and then if an algorithm does not perform efficiently on some input, you have to figure out how to modify the algorithm. Well, in this case, the conclusion here is LR1 parsing works better with left recursive grammars. So let me just stick to the left recursive version of a grammar, because LR1 parsing works better on these. Okay, so in this case, of course, there is no difference between, the left recursive and the right recursive. They are equivalent. They are two equivalent grammars, but the LR1 parsing algorithm generates a totally different table, and it parses the string totally differently. Okay, any other questions? Okay, so. I wanted to talk about, so this is the LR1 parsing. I'm still grading the LR1 parsing. I'm not done grading, the LR1 parsing question. I'm still in the middle.